Welcome all to the short video lectures on the Chemical Engineering Thermodynamics 2 course. I am Naren from SASTRA deemed to be University. This is part 2 of the lecture 2, where we are discussing on fundamental property relationships. Now in the lecture L2.1, which is the part 1 of this talk, lecture 2, we saw that the total property of a solution can be written in terms of the operating conditions that we say it as pressure, temperature and the actual moles of all the components. And the task we had before we took a break of the lecture is how to represent the change in the property of the system. So we want to write change in the total property of system based on this expression, based on this functional expression or the functional notation rather I would say of the total property of the system. So I would expect that you could have guessed it from your knowledge of differential calculus, but if otherwise you can just follow this lecture to get what is expected of the system. So for any variable given, like say phi, d phi represents a finite infinitesimal change in the system that is induced by changing the constituent variables, the independent variables that makes this dependent variable. So in max we know that, like say if I have a dependent variable phi, which is a function of, like say, independent variable x, y and z, then infinitesimal change that can be represented in terms of changing these independent variable can be written in terms of d phi. Now this change in d phi can be because of change in x, change in y or change in z. And that's where you would have studied the total differential concept in mathematics, which says that the total change that is expected in phi is because of the change that is there in x, because of the change that is there in x, and how much is the change in x have induced the change in this variable, plus what is the change in y and how much is the change in y have caused a change in the variable phi, plus what is the change in z and how much is the change in z has caused a change in value of this variable. I repeat, let's take, this is all based on the concept of differential calculus. So if we have a dependent variable phi, which is a function of three independent variables x, y and z, and let us assume this function is continuous, so that means this x, y and z can take continuous value in a given space domain system that we are talking of. That means any change in x, any change in y and any change in z will result in change in phi. So the total change in phi can be represented as a change in x, right? So this represents the change in x, and how far is the change in x affects phi. The change in y, how far is the change in y affects phi, and the change in z, and how far is the change in z affects phi. So this is how we measure the total change. So if we can take clue from this, so all we have to do is apply now this entire thing to what we have seen in a thermodynamic variable m. So we are going to use the same concept but apply it to a different set of variables. Let me just do that. So that means we have mt, the total variable, the total property of the system is given as the number of moles of the system times the molar property, which is a function of Pt, n1, n2 and so on till nn. If that is the case, then the total change in the property of the system, the total change in the property of the system, which is also equal to d of Nm, is given as the change in the pressure of the system. So, the change in the pressure of the system, and how far is the total property changed because of the change in pressure. So, that is given by a partial derivative of dou mt divided by dou p. So, the change in pressure and how far is the change in pressure changed the system property, plus the change in temperature and how far is the change in temperature affected the total solution property. Then you can have a change in number of moles of only the first component. Only the first component could change. We saw this in the previous lecture part 1, that I changed only the third component. So, similarly one can do change in any component. So, what is the change in the first component? Sorry, I have to put here the conventional notation of the change in the first component, and how much is the solution property changing by changing the first component alone. Now, similarly you can extend what is the change in the second component, how far is the change in the second component changing the solution property, and so on. This keeps extending for all the components. So, in general we can write d of Nn, and this is dou mt divided by dou of Nn, right. So, this is a functional representation. So, this is a functional representation of the change in the system property. So, this primarily denotes the change in the total property M. So, the total property here we have written it as M, but it could be like, as I said, enthalpy, entropy, volume, Gibbs energy, either Helmholtz Gibbs energy or the Helmholtz free energy or the Gibbs free energy, the enthalpy, internal energy, entropy and volume. So, this M could take any of those. This is the total change in the total property of the system. This change in the total property of the system is given by, this is the change in pressure. So, this denotes the change that we expect in pressure. So, this is the change we expect in pressure, and this term as a whole. So, this term as a whole denotes, what is the change in the property of the system, so of the solution, for change in pressure. Similarly, this term denotes the change in temperature, and this term as a whole, denotes what is the change in the total property of the system for change in temperature. Now, this term denotes what is the change in the total number of moles of species 1. So, this is if we write, so this is only the change, is a change in mole numbers of species 1, whereas this partial derivative term tells out what is the change in property of the solution or the system as a whole for change in moles of species 1. So, like this we can write, and we can extend this to all the n component system. Now, if you observe these terms, so if you observe the terms, let's say from here till this end, they are almost similar. So, they are almost similar. Only thing is, here it is component 1, here it is component 2, there will be component 3, and so on and so forth till component n. So, they are almost similar. So, that means we can write this in generic as follows. So, that means we can write this 2.2, just write it. So that means that the terms that we are talking, like T of mt divided by dn1, similarly d of mt divided by dn2, there are like terms like this. So this can be written in general as one single term as dou mt divided by dou ni, then we can say as dni. So where n denotes, sorry, so where n denotes the mole of that particular species I, and this is written as summation of I equal to 1. So that means number of moles is 1 to n. So this is how we can represent in general of all these terms that we see here. So if you carefully see all these summation terms, they are almost similar. So that means we can collectively represent them as this here. So where again this, if you recollect, this talks about change in moles of species I in that solution system. So in the solution system, whereas this entire term talks about what is the change in the property of a solution for a unit change in moles of species I, right? So if you make use of this, we can rewrite the expression that we saw earlier as follows. So we can use of this generic expression and then rewrite dmt, which is d of the total change that we expect here, as dou mt by dou p into dp plus dou mt plus dou t into dt plus sigma of I equal to 1 to n dou mt divided by dou ni and dni. So this is how we can simplify. Now, is this complete? There is some more things that is to be included to make it more appropriate. So there are some things hidden in these terms. Can you just identify those? Now, when we say that pressure is changing and this is a contribution of pressure, what about the other terms? Because if you recollect, the total property is given as function of not only pressure but its pressure, temperature and all other components till n. So that means what are the other components doing here? That means it is indirectly means that when you talk about this change with respect to pressure, the temperature and the moles of all other components are remaining constant. So in this derivative, in this partial derivative, the temperature and the number of moles is not changed. So that means when you talk about the change in terms of temperature, the pressure and the moles of all other components are not changing. So that means you talk about only the change in temperature and how far is the change in temperature is affecting the change with respect to the solution, but you have to keep P and N constant. Now if you extend that logic here, Pt is constant, but remember it's not here N, it is like Nj not equal to I. Everything other than the I component is changing. So let me explain this further. So suppose if you take this, so when I write like say for example gmt for with respect to let's say third component, I mean pressure is fixed, temperature is fixed, every other component other than the third component, so every other component other than the third component should be fixed. So that means n1, n2, then let's say n4, n5 till nn. Now we don't usually write all such a big list, so we write as Pt and we write Nj where j is not equal to I. So I is already an index that is given here, so that means we symbolically indicate that the change is only with respect to that particular species and not with respect to the other species. So this represents the symbolic, the functional notation of denoting a change in the solution property with respect to pressure, temperature and the constituent moles. Now this property, what we write here as a very interesting name, and this in thermodynamics is called as partial molar property. So what is partial molar property? So this change in moles, the change in the property of the system to the change in moles of ith species, keeping pressure, temperature and all other moles other than I as constant. So this term is called the partial molar property, and it is usually given a letter Mi bar. This is denoted by Mi bar. So this is the partial molar property of a component I in the system. Suppose let us assume a system has 4 components. So that means a system has 4 components. If I say what is the partial molar property of the third component in the system with respect to a solution, which means what is the change in the total property of the system due to the change in the third component. So that means I am talking about partial molar property of component 3. So I have to measure the system property with respect to the moles of the third component, keeping pressure, temperature and moles of all other species other than 3. So that means moles of the first component, second component and fourth component, N1, N2 and N4 will remain fixed. I can only change the third component and measure the total property of the system, and this partial derivative is called the partial molar property. Now using this notation one can write, one would be able to write the change in the total property of the system to be as dou m by dou p. Now here temperature and moles of all the species are constant, change in pressure plus change the partial derivative, the change in the property of the system with respect to temperature. Here pressure and all moles are constant, this is for the change in temperature, plus sigma of for the component 1 to nth component, this is the partial molar property of that component and the respective change. So this is how we represent the property change in a solution. So this gives a property change in a solution, and we have seen that this term denotes the partial property. Okay, this is a partial molar property, so this is a partial molar property of component I. Now we will break here for a discussion, but before I take a break for discussion, I would want you to think on what if T and P remains constant in a system, what will happen? Or rather, if T, P and composition also remains constant in a system, okay, what will happen? So here you have this equation which represents the total change in the property of the system due to the change in pressure, temperature and the moles. Suppose if you say that the pressure and temperature remains constant, what would happen? and if you say that, like say everything remains constant, then what would you expect? So you take on this as a trigger, and we will see what would be the deductions of these assumptions in terms of the property relationships. Thank you for watching this video. See you. Bye.